Hello everyone. Today we're going to discuss statistical intervals for single sample, this time all about proportions. Estimating the proportion P. To approximate the binomial proportion P, we're going to take note that mean is NP and the variance is NP times 1 minus P. If we will be dividing this by n, both numerator and denominator by n, it would be x over n minus p all over np times 1 minus p, or all over square root of np times 1 minus p all over n squared. So that would become square root of p times 1 minus p over n. This is approximately standard normal. Um, in approximating the confidence interval on a binomial proportion, if p hat is the proportion of the observations in a random sample of size n that belongs to a class of interest, an approximate 100 of 1 minus alpha percent confidence interval on the proportion p of the population that belongs to this class is given by p hat minus z of alpha over 2 square root of p hat times 1 minus p hat over n. And for the upper limit, it would be p hat plus z of alpha over 2 square root of p hat times 1 minus p hat over n, where z of alpha over 2 is the upper alpha over 2 percentage points of the standard normal distribution. This is the traditional approach in approximation for the proportion. So there are two approaches basically. The first one is taking note that p is approximately equal to p hat. That's why it becomes this formula. However, take note that p hat is, we are approximating p, so we should not be using p hat alone. So there should be a correction factor. So that is resolved by a Gresticle confidence interval on the proportion. So this is the resulting formula. So for upper control limit, there is a correction of z alpha over 2 over 2n and so on. For the sample size of the estimation for proportion would be n is equal to z of alpha over 2 over e squared times p times 1 minus p. Another approach in choosing n uses the fact that the sample size from the equation will always be a maximum of p equal to 0.5, and p times 1 minus p would be less than or equal to 0.25 with the equality of p equal to 0.5. So the highest sample occurs when the proportion is equal to zero point 0.5. So when it is unbiased, so that would be the largest sample that we can take. So if we are not given with the initial proportion, if we are not going to assume proportions, we're going to use um, p times 1 minus p is less than or equal to 0.25. So the p times 1 minus p would now be 0.25. So for one-sided confidence, we don't divide alpha by 2. So the lower bound would be p hat minus z of alpha over square root of p hat times 1 minus p hat over n. And for the upper bound, it would be p hat plus z of alpha times the square root of p hat times 1 minus p hat over n. As an example, The fraction of defective integrated circuits produced in photolithography process is being studied. A random sample of 300 circuits is tested, revealing 13 defectives. So N is 300, X is 13. Calculate the 99% confidence interval on the fraction of defective circuits produced by this particular tool. Calculate the 99% upper confidence bound on the fraction of defective circuits. So we solve the other two problems later. So for the first one, we have N is 300 and X is 13. And then 1 minus alpha is 0.99, giving us alpha over 2 is 0.005. This is this would give us Z of 2.326. So if we will be having X is 13, N is 300, and 99% confidence interval. So alpha is indeed 0.01 and alpha over 2.005. Observing the values for the confidence interval, so Z is 2.576 for alpha over 2 of 0.005. So substituting and plugging it on the formula, we have 1.3% up to 7.36%. Calculate the 99% confidence bound on the fraction of defective circuits. So that means we don't divide it by 2. So alpha is 0.01 and that is 2.326. For the upper bound, we use positive 2.326. So the upper limit would be 0.07068. So it is closer to the mean. Next one. Compute the 95% confidence interval. So 1 minus alpha is 0.95. Using both for the proportion of defective items in a process when it is found that N is 100, X is 8. So X is 8 and N is 100. And for the confidence bound 95%, we will be having um, for 95%, 5% would be alpha. So alpha over 2 is 0.025, which would give us a Z of 1.96. If we will be using P hat minus Z of alpha over 2 square root of P hat 1 minus P hat over N, this would be the resulting value for minus, and this would be the resulting value for plus. Next, how large a sample is needed in exercise 9.52 if we wish to be 95% confident that our sample proportion will be within 0.05 of the true proportion defective. So we assume that the proportion is 8 out of 100, so 0.08 for 95% confidence interval, and then an error of 0.05, we have 113.09. We always round it up. That's why we should be having 114. Another problem. A manufacturer of MP3 players conducts a set of comprehensive tests on electrical functions of its product. All MP3 players must pass all tests prior to being sold. Of a random sample of, so this is N, 500 MP3 players, 15 failed. So this is X. 15 failed on one or more test. Find a 90% confidence interval, so 1 minus alpha is 0.9, for the proportion of MP3 players found from this population that pass all tests. So we just plug in 15, 500, and 90. So for the first formula, for method 1, a 0.05 alpha would give us z of 1.645. So this is the resulting confidence interval. But if we would just be trying method 2, the agrestical approximation, so there would be correction factors for the standard error, and this would be the confidence interval. A study is to be made to estimate the percentage of citizens in a town who favor having their water fluoridated. So there's no background regarding this study. How large a sample is needed if one wishes to be at least 95% confident. So alpha is the confidence level is 95%, and it is within 1% of the true proportion, so 0.01. If we don't have an idea of the true proportion, so we use 1/2. Or we use the second formula for the sample size determination. So the answer is 9604. So in estimating confidence interval, so there are different parameters that we would be estimating. We have mean, variation, so variance and standard deviation, and proportion. When do we use mean? When do we use z-score? So if sigma is known, if there is sigma on the problem, we use z. If n is greater than or equal to 30, we use z. But we will be using t when sigma is unknown and n is less than 30. And then we use chi-squared for variances, and then the binomial proportions for the percentages or population proportions. So the interpretation for confidence interval, the confidence interval simply provides error bounds on the parameter. So what would be the lowest possible and highest possible value of the parameter? The values contained in the interval should be viewed as a reasonable values given in the experimental data. So how do you expect your true proportions, your true means, and your true variances to be of what value? So your estimator is the probability that your estimator falls between the lower limit and the upper limit is your 1 minus alpha confidence. That is your confidence level. So if your variance is known, we use z, and the sample size determination, the formula. Upper bound, lower bound. If the sample size is small, we use t distribution, and then for variances, we use chi-squared. For proportions, we have this formula, and then the alternative, the more exact and more exact approximation, the agrestical for proportions. These are the references used to create this lecture.